All right, it's about time to start up again. Our next speaker is going to be Madeleine Brandt, who will tell us about top-weight rational cohomology of AG.
Thanks for the introduction, and thanks to the organizers for putting together this lovely conference and for having me here to speak about this topic. So today I'm going to be speaking about the top-weight rational cohomology of AG, and this is joint work with these collaborators, so Juliette Bruce, Melody Chan, Margarida Melo, Gwyneth Moreland, and Corey Wolfe. And this collaboration started at a conference at ICERM. So this was supposed to take place in person in the summer of 2020. And as part of this, Melody and Margarida were leading a group where they had planned this project. And of course, the conference ended up taking place online, but it still led to a really productive research collaboration. So they were the ones who sort of organized this project. And yeah, let me go ahead and get started. So I was told, and I won't name any names, but I was told by someone that my abstract was scary. So this slide is sort of meant to set the tone for the talk and say that I hope that this talk won't be scary. And if you have any questions, please feel free to interrupt me. Or if you have questions afterwards, you can ask me, like, what is this creature? Yeah, so let me go ahead and get started with the actual math. So,
poodle.
Sorry, he is part poodle. Part poodle. Okay, so let me just start off. So, what is AG? So I'm going to let AG denote the moduli space of principally polarized abelian varieties of dimension G. Yeah, okay, so I promised that the talk wouldn't be scary, so why did I start by saying something that was not in English? So let me just say, sort of, in case anyone here doesn't really study moduli spaces, let me just say, like, intuitively, what is a moduli space? And I'm writing this separately because I'm going to say these words probably like 100 more times in the next 45 minutes, so in case you forget, then it's going to be written right here. So to me, a moduli space is going to be just some space whose points correspond to isomorphism classes of some type of object you're interested in. So a moduli space is a space whose points are in bijection with isomorphism classes of some objects you are interested in. So for me, in this talk, the objects that I'm interested in are something called principally polarized abelian varieties. And these actually aren't really going to come into play in any detailed way, but I'll just give you something to picture in your mind whenever I'm talking about these. So these are algebraic varieties that carry some kind of group structure. And I think the example of elliptic curves is a good one to keep in mind. So maybe this is familiar to some people, but you have this group law structure for elliptic curves where you can take 2 points and add them and get another point on the curve. So it's an example of an abelian variety. Okay, and then our goal in this project is to study the rational cohomology of this space AG, and we're going to use something called tropical geometry. So rational cohomology, whatever that is, that's just some invariant that we're interested in computing about this space. And we're going to go about it using tropical geometry. Okay, so this talk is sort of going to be in 2 parts. So the first part, I'm sort of just going to give an overview of a recent research direction that a lot of people have been interested in, and I'm going to just give this the sort of blanket title of tropical geometry for cohomology. So I'm gonna, in the first half of the talk, just give a really big overview of this sort of area of research and give you an idea of how this works and what some of the results that people have computed in this area are about. And then in part 2, I will hone in on the specific case of AG. So doing this for AG. Okay, so in the first part, let me just say a little bit about what is tropical geometry. So maybe you've heard of it before, maybe you haven't, but the sort of catchphrase that everyone says when they say what is tropical geometry that you'll hear a lot is that tropical geometry is a combinatorial shadow of algebraic geometry. And I like this catchphrase because I think it paints a picture of what is sort of the right idea. So given some algebraic variety, like maybe this elliptic curve, tropical geometry gives you a way to associate to that. It's tropicalization, which is just a polyhedral complex. And the idea of this is that this procedure of tropicalization somehow you lose some information about the variety, but hopefully you've retained enough that when you study this simpler object, you can still learn something about the algebraic variety that you're interested in. So in this talk, the sort of example of a piece of information that we're going to learn is on the right-hand side, I'm going to be looking at some homology groups. And then what I'm going to recover on the left-hand side is something called the top-weight cohomology. Okay, so that's tropical geometry. Now let me talk a little bit about moduli spaces, tropical moduli spaces. So in the beginning I said that a moduli space was a space whose points are in bijection with isomorphism classes of some object you're interested in. So what is a tropical moduli space? So let's say M is a moduli space for varieties of some type, just type P. So like in this talk, type P might mean abelian varieties, but like another example that people might be more familiar with is smooth curves. So then M itself is a variety, and I'm going to let M bar be a compactification. So there's sort of 3 spaces that you might think to associate to M, 3 tropical spaces. So if I ask you what is the tropicalization of M, I think there's a lot of correct answers. So the first one might be, well, you told me that M was a variety, and on the previous slide I told you that tropicalization tells you how to take a variety and associate its tropicalization. So that's what this first one is. We're just going to tropicalize the variety M. Then the second thing you might do is say, well, M parameterizes varieties, so let's tropicalize those varieties and see what types of polyhedral complexes we get out of that, and then put all of those polyhedral complexes into a moduli space to get some kind of combinatorial moduli space. And we might call that the tropicalization of M. So it's like a combinatorial moduli space that's parameterizing the tropicalizations of things in M. And then the last one that I'm going to talk about more in this talk is something called the dual complex associated to the compactification. And really this is sort of a technical point, but I really mean the cone over this dual complex. And I will define this in more detail in 2 slides. So the point here is that if we have a moduli space M from algebraic geometry that we're interested in, there's sort of 3 different spaces that you might consider as the tropical version of that moduli space. However, the cool thing is that typically these three spaces actually coincide. And this has been studied for a lot of moduli spaces, and this is just a couple of my favorite examples. So one, the moduli space of stable end-pointed curves is studied, the tropical version is studied in papers by Abramovich, Caparaso, and Payne, and also many other papers. This is just one place you might look to learn about that. Then also the space of admissible covers, studied by Cavallari, Marquig, and Raghunathan. And then in this talk, we're going to be looking at the space of abelian varieties. And the tropical version of this is studied in papers by Brandt, Melo, Viviani, and Chan, Melo, and Viviani. And then there's many, many other examples of moduli spaces that have been studied tropically, and there's many nice correspondences along these lines. Okay, so maybe I should pause. Are there any questions so far? Okay, so now I'll define the dual complex as promised. So if I have a smooth variety X and a compactification of it, which is simple normal crossings. So this is just a technical assumption that sort of tells me that the boundary has nice enough combinatorics that I can do something with it combinatorially. So this just means that the boundary has smooth irreducible components that themselves intersect transversely. Okay, then how do I define this dual complex delta associated to the compactification X bar? So this is a simplicial complex where the vertices correspond to the irreducible components of the boundary. Then I'm going to make an edge whenever I have an intersection of a pair of irreducible components. Then the next step would be that I make a triangle whenever there's a triple intersection, and so on. So whenever you have an intersection of the irreducible components, then you just make a simplex of the appropriate size. And that is the dual complex. Okay, so now I'm going to state the comparison theorem. So far we've sort of talked about classical moduli spaces, we've talked about tropical moduli spaces, and we've talked about the dual complex. So now I'm going to show you the tool that we use to associate something about the tropical space to something about the classical space. So this is the main technique for using tropical moduli spaces to understand the topology of their classical counterparts. Okay, so this is a scary formula. So we're going to let X be a smooth separated Deligne-Mumford stack. So in all the examples that I'm going to show in this talk, this will just be some moduli space that we're interested in. And then X bar will be a normal crossings compactification. Then I have an isomorphism between two things. So what are the things? On the left-hand side, we have something about this dual complex that I presented, that I defined on the previous slide. So what we're doing here is computing the reduced homology of that dual complex. Now, what I want you to observe about this left-hand side is that since this is a simplicial complex, hopefully you know a list of all of the simplices that make it up. And so your favorite algebraic topology textbook will be able to help you compute this quantity. So this left-hand side is like completely computational, combinatorial, and it has like very little to do with algebraic geometry, probably. Then the right-hand side, so what is this? This is something called the top weight cohomology, which I'm not going to define, but this is just some piece of the cohomology of X. Okay, so we've associated the homology of some simplicial complex to the top weight cohomology of the moduli space X. Okay, and as we saw before, this is sort of thought of as a tropical moduli space. So now we're in a position to sort of think about just these tropical objects and do these combinatorial calculations to learn something about the topology of X. And this statement follows from work of Madeleine. Okay, so now let me show you some of the things that people have been thinking about using this comparison theorem. So the first two papers that sort of started off the interest in this area were these first two. So the first one is a formula for something called the SN equivariant top weight Euler characteristic of MGN. And this was given by Chan, Faber, Galatius, and Payne in 2019. And then they also studied the top weight cohomology of MGN in a paper by Chan, Galatius, and Payne in 2020. And following that, there was more work done on the space M2N, and this was studied by Yoon in 2020, and then also by Bibi, Chan, Gadish, and Yoon in 2021. And then in this talk, we're going to talk about the top weight cohomology of AG. And then something called weight 2 cohomology is studied by Payne and Willwalker in two papers in 2021. So what is weight 2? So just going back quickly to this, I said that this was something called top weight. So you might wonder if that means that there's other weights, and there are. And people have sort of started thinking about how to enhance these computations so that you can look into other weights. And then the top weight Euler characteristic of MGW, another moduli space, is studied by Kanan, Lee, Serpente, and Yoon in 2022. And then the last thing that I wanted to mention is that in a current collaboration with Melody Chan and Sarth Kanan, we're studying the SN equivariant top weight Euler characteristic for hyperelliptic curves. So why did I list all of these out? This is just to say that this is like a very recent area of study that people are very interested in. So if you find this talk inspiring, or you have other ideas about things to compute with this, I'd be happy to talk more. Yeah?
Could they all go like through the identification with the simplicial complex?
Good. Other questions? Okay, so this is just a slide to pause and say now we're going into part 2 of the talk. So we've sort of finished talking about, this is like the end of my my big overview on like how do we use tropical geometry to do cohomology calculations. And now I will go into the specific example of how we did this for AG. Okay. So what was known previously about the cohomology of AG? So in 1962, Igusa computed the cohomology of A2. And then in 2002, Hayne computed the cohomology groups of A3. And then from work of Hulek and Tomasi, you can get the top weight cohomology, which is what we're computing, for A4. And then in 2009, Gruszewski asked the question, does AG ever have non-zero odd cohomology? So you'll notice here all of the homology degrees that appear are even. Okay, so now I'll just show our main result, and then I'll talk about how we did this. So our main theorem was to give the top weight cohomology for G between 5 and 7. And you'll notice that we do actually see cohomology in some odd degrees. So this answers Grushevsky's question because it says that, yes, we actually do see some odd cohomology for AG in these specific places. Okay, so let me get a little bit into the details of how we did this. So what is a tropical abelian variety? So I'm going to give a definition. So a principally polarized tropical abelian variety is going to be a pair consisting of this real torus together with a Q. So this Q is the data of the principal polarization. And Q is going to be a positive semi-definite quadratic form on RG with kernel defined over Q. So for example, in this box, the color is visible. I have a little example. So if G is equal to 2, then you might have this quadratic form Q, x squared plus xy plus y squared. And that is identified with this symmetric matrix. Okay, so that's a principally polarized tropical abelian variety. And then we say that two of these things are isomorphic if there exists an X in GLGZ with X transpose QX equal to Q prime. Okay, so if I can get from one to the other via a GLGZ, then they're isomorphic. So let's put all of these principally polarized tropical abelian varieties into a moduli space. So really, they only depend on this thing Q, which we can write as a matrix, as a symmetric matrix. And we know when they're isomorphic. We have a group action that tells us when two principally polarized tropical abelian varieties are isomorphic. So we're going to just take this space, omega G RT, which is the space of positive semi-definite quadratic forms with kernel defined over Q. So all the possible matrices Q is this set, and we mod out by the action of GLGZ. And then that gives us this space, AG trop, whose points correspond to isomorphism classes of principally polarized tropical abelian varieties. Okay, so now what do I want to do? So thinking back to the comparison theorem, I now have the tropical space, and I want to compute its reduced homology. So how do I do that? We don't know really anything about what this space looks like, but if I could give you a decomposition of it into polyhedra, then you would be able to compute its homology. So that's what we're going to do. We're going to decompose AG trop. So we're going to think about the space of positive semi-definite quadratic forms. We're going to view this as living inside of R to the G plus 1 choose 2. And we're going to do that by identifying this space with the space of symmetric matrices. So looking back to G equals 2, if I have a symmetric matrix, I can think about this as, so we have entries A, B, B, C, and I just remember the top 3 values, and then that gives me a point in R3. So let me draw a picture. So we know something about what omega G RT looks like, because if I take any point in omega G RT, so this is positive semi-definite quadratic forms. So if I take a point in omega G RT and scale it by any positive real number, then I stay inside of that, which means that it's a cone. So let's imagine that this blackboard is R3, and this is the origin. So that means that whatever omega G RT looks like, it's some cone in R3. And I'm going to just picture that as an ice cream cone. So this is R3. And then this is omega G RT, which is positive semi-definite quadratic forms with rational null space. Okay, so that's some sort of cone, and we have this GLGZ action on the cone, so, and I guess in this case G is 2. So GL2Z acts on the cone. Okay, so there's a theorem due to Voronoi which says that we can actually decompose omega g RT into a set of polyhedral cones, sigma, which the set of polyhedral cones is going to be called sigma p, and they're called perfect cones, such that we have the following like super nice properties. So the perfect cones cover omega g RT. Next, the perfect cones are closed under intersections and taking faces. So that's another reasonable ask. And now we're going to ask two things that make them behave nicely with respect to the GLGZ action. So sigma p is going to be closed under the GLGZ action. So as I act on these cones with my GLGZs, we're going to stay inside of the set of perfect cones. And then the last one, which is like, I think really amazing, is that if I take all of my perfect cones, which a priori might be like an infinite list of cones, when I mod out by the GLGZ equivalence, I get a finite list of cones. Okay, so just one side note. So this set of properties is called, if you have a set of cones that satisfies those properties, it's called an admissible decomposition of omega g. And there's more types, there's more known admissible decompositions than just the perfect cone decomposition. But the perfect cones were advantageous to us computationally because they're sort of, there's less of them than in other decompositions. Okay.
You're asking for the matrix to be positive?
Positive semi-definite.
Positive.
Yeah.
But maybe I didn't understand the claim, but you literally mean polyhedra, like with flat inequalities defined? I mean, this looks like a curvy space naively. Like in a 2 by 2 matrix, it looks like AC minus B.
Yes,
A bigger than 0 and AC
I'll
minus B
draw
squared
the
bigger than
cartoon, but there's one coming. So basically how this works when G is equal to 2 is I'm going to like fill this space with like infinitely many triangles.
Oh, now I got it. No, okay, sorry.
Yeah.
Now I got it. No.
So this is
Right.
like,
No,
yeah.
thank you.
So this is what
confused.
the,
It looks curvy, but it's covered with the...
there it is, yeah, okay.
Oh, thank you. Okay.
So yeah, it just gets completely populated with these triangles.
But
So
you're saying you can cover the whole thing starting from some basic triangle and just GL, just doing these.
So there's finitely many of them. Yeah, there's finitely many.
And then you act with GL2 and that covers everything else.
Yeah. So in the case G equals 2, there is only one like maximal size perfect cone up to GLGZ equivalence, but that's just like because 2 is small. When you go in higher dimensions, there's more of them. Yeah. So that's a good question, just to kind of clarify like the geometry of what we're talking about. So here's like an example. So there's a couple of matrices living on the boundary of this space, and the sort of cone that they correspond to. So this is a picture of the perfect cone decomposition for G equals 2. And one just remark is that there's only one perfect cone of each dimension up to GL2 equivalence when G is equal to 2. So really in this picture, like you should be able to find an element of GLGZ that sends this to this and this to this. So there's only one ray, one cone of dimension 2, and one big cone of dimension 3. Okay, so now that we've decomposed AG trop into this finitely many polyhedral cones, what we're going to do is apply the comparison theorem. So there is a compactification of AG which I'll call AGP prime, such that the dual complex corresponding to that compactification is omega G mod GLGZ up to, like, I want to take this L, which is just the link. So what is that? It's just, instead of looking at the whole cone, I'm just looking at the slice. So just looking at what's going on inside of this oval. And it has, and this thing comes with the polyhedral structure given by P prime, which is a refinement of sigma GP. And that's just, this is a little bit technical, but basically originally I asked that for simple normal crossings compactification, and the compactification corresponding to the perfect cone decomposition doesn't turn out to be simple normal crossings, but you can take a refinement to get one that is. Okay, so then by the comparison theorem, what do we have? So on the left-hand side, we have the top weight cohomology of AG. So this is the thing that we want to compute. And then on the right-hand side, now we're translating this into just studying the reduced homology of this space that we've been talking about, which is now a purely combinatorial thing, and we know how to decompose it in terms of a list of perfect cones. Okay, so now we want to compute this reduced cohomology. So this can be done via a chain complex consisting of vector spaces with bases indexed by these cones. So for example, if you had to do this on your qualifying exam for the Klein bottle, how would you compute the homology of the Klein bottle? Well, you'd first write down sort of a way to triangulate it, and then you would count up how many faces and how many edges and how many vertices are there, and then you could compute its homology. So that's sort of exactly what we're doing here. And sort of the last missing ingredient at this point is that we need to know, like, what are all of the perfect cones and what is the differential in this chain complex. And it turns out that similar chain complexes were studied by Lee Charba and Elbaz, Vincent, Gangle, and Soule. So they were interested in something different, so their chain complexes are a little bit different from ours, but they were similar enough that we could, like, adapt them for use in our computation. So we adapted their computations to get our main result. Okay, so now just a recap. So we saw in the first half of the talk how tropical geometry is sort of used to do these top weight cohomology computations. And then we use this idea to compute the top weight cohomology of AG. And you do this by using the comparison theorem to relate the top weight cohomology of AG to the reduced homology of the boundary complex. And this boundary complex, in this case, is identified with the tropicalization of AG, and it comes with this decomposition by perfect cones. And that's all I had planned to say, so thanks for your attention.